Welcome to Pomodoro Joe for Friday, February 10th, 2023. Today we're doing LeetCode problem 1162. As far from land as possible. It's a medium problem. And the problem statement says, given an n by n grid containing only values 0 and 1, where 0 represents water and 1 represents land, find a water cell such that its distance to the nearest land cell is maximized, and return the distance. If no land or water exists in the grid, return -1. The distance used in this problem is the Manhattan distance. So by that they mean up, down, left, right. You just follow the grid. Okay, and our constraints. The grid is between 1 and 100 on a side, which is a fairly reasonably sized grid. It's not that big. All right. So with that, we'll put 25 minutes on the Pomodoro timer and get started. Now for this, unfortunately, I don't have a great algorithm in mind. I have one that we can optimize later, but this is not going to be pretty. Here's my plan. This grid has just zeros and ones in it. Ones represent land, 0 represents water. We will find all the land cells in the grid and then essentially like drawing an outline around them. So you can imagine if this were a map and you had some land and some water, you draw an outline around the land, filling in some of the water along the way. So that's basically what we'll be doing. We'll find these land cells and then look around for any water cells that are touching that land cell, and we'll fill it in. We will make it landfill or something. And then we'll have to do multiple passes. So in the first pass, we will fill in just the first round of coastline, that first outline, and then we'll do a second pass and we'll basically grow that outline even bigger, and we'll make a new one, a new one, a new one, until we run out of water in our grid, and then we're done. So this is multi-pass. It's not optimized at all, but I think it will work. I hope it'll work. All right, let's give this a shot. So we start with the result, and that's equal to -1, just in case we don't have a good answer. And we will return the result at the end. Okay, now one thing that I like to do, this is not strictly necessary, but I think it's good coding practice. So I will make a copy of the grid. I don't want to modify the existing grid because it's generally not a good idea to mutate the input value unless you're explicitly told it's okay. Now in these problems, it's not a big deal, but if you're working in a professional coding capacity, you probably want to make sure that anytime you modify those inputs, that's an expected side effect of your function. So for us, we'll just call it working grid. And we're just making a copy of the input, so we don't have to worry about mutating this. Okay, let's see. And we will have to do multi-passes on this. And for that, we need to know when we're done. So I'll have some done and we'll set it to false. And we'll say, well, we're not done. We'll keep going. So the first thing I'll do is set done to true. I set it to true at the beginning just so I don't end up in an infinite loop. We will find out later if there is water in the grid still, then we'll set done to false because we're still working on it. If we go through this whole process and we don't hit any water, then done is true. We don't need to do anything, and it breaks out of our loop. So we will go through our grid. So for y in range, it's going to be the length of the grid. And then for x in range, length of grid 0. So in this case, y is basically the same as your row, and x is the same as your column. Now I'm doing this in, I guess, screen coordinates, where 0, 0 is the upper left corner, and y gets bigger as you go down, and left gets bigger as you go to the right. All right, so let's grab, so this should traverse our grid. Let's grab the value at our x and y coordinate here. So that's the working grid. All right, one more thing to note. rows come first and then columns, so we do y and then x. So the value at our coordinate xy is working grid at yx. Okay, now we are looking for land right now. We're looking for land so that we can outline it. So if our value, now you could say is equal to 1, but what we'll be doing is we're creating these outlines or doing this land fill. So we're going to look for anything that's greater than 0. That means it could be the original land, which will be 1, or it will be our landfill, which will be 2 and above. Okay, so if we do find some land or some landfill, now we need to check up, down, left, and right for any water. Okay, so what is our up coordinate in this case? Well, we have the same x, but we will do y minus 1 because I'm using screen coordinates where 0, 0 is in the upper left and y gets bigger as you go down. So up is actually y minus 1. And we want to make sure that we don't go out of bounds, so we better check to see if y is greater than 0. Otherwise, we don't have an up. Okay, so that's our up. Now we need a down, a left, and a right. So it's basically the same procedure here. So let's see, up, down, left, and right. And now up is going to be y minus 1, down is y plus 1, left, we keep the same y, but we say x minus 1. And right, we keep the same y, but it's x plus 1. And now for our checks here, we have to say not y is less than 0. So if we're looking down, we may have to make sure that y is less than the length of our grid minus 1. All right. Now that we have our up, down, left, and right coordinates, I like to put these into an array because I will be essentially going through each one, checking to see if it's water, and then doing something. All right, so I'll go up, down, left, and right, and then for every coordinate in our chords here. Now I'll check the value at that coordinate in our working grid. So I'll call this the coordinate value. And in fact, I'm going to break this out into coordinate x and y just because it makes it a little bit more readable here. All right, and remember when we do our check, we have y and then x. Okay, so I get the coordinate value at the adjacent grid coordinate. So we're looking up, down, left, and right from our current grid. Now we're looking for if that is water. So if our coordinate value is equal to 0, well then we better fill it in with some land. So in that case, we will grab this whole thing and we'll change its value to our current value, the value at our current land grid, plus 1, because it's one step away from our land. Now, one thing that I haven't mentioned, we will eventually have to correct for our coastline, our original coastline, because every initial coastline coordinate value that was 0, some water, it's technically one step away from our coast. But we're adding 1 to our coastline, which is 1, the land. So our original land will be value 1. Our first outline will be value 2. Our next outline will be value 3, and so on. Technically, that's 1 more than the step away. It's technically 1 greater than the number of steps it takes to get to land. So we will have to correct for that at the end. Okay, so we've got our coordinate value, we've checked that it's water, we're filling in with some landfill, and because we found some water, we will set our done equal to false. We are not done, we made some change. Okay, finally, we are going to eventually fill in all of that water and we'll be done. We still need to get our result here. So for every row in our grid, not our grid, our working grid. That was a close one. We will find the maximum of that row. So let's see the row max. And then we will check that against our current maximum for our result. Okay, and then we found the maximum value in our entire grid. We need to subtract 1 from it when we return, and we need to do one more thing. That is only if our result is greater than 1. If we didn't get anything outside of our land or our water, so if the grid was entirely water, we'll have zeros. If the grid was entirely land, we'll have ones. So only if we get something that had some water, which will be at least 2 and above, then we can return our result. Otherwise, we need to return -1. And with that, I think we might be done. I'm nervous about this. There actually might be one more thing here. We need to make sure that we don't have a shorter path to land. We might need to check here. If we have a lower value at our working grid than, no, a higher value at our working grid than what our current value is. I'm not totally sure that that's needed. Let's try running this just to see. Oh, right. I wasn't checking here. I should have said if we have a chord. So in this case, because I've already done a bunch of work and I don't want to re-indent, I'm going to say if we don't have a coordinate, we'll just continue. Some of these coordinates can be none. All right. And actually, while I'm in here, I am actually going to make this change because I do think it's necessary. So if we found some water, or the value at our coordinate is greater than our value +1, then we can actually get to this water, or this water space can get to our land sooner than we thought, so we better replace it. Okay, let's try that. Okay, it works. I am super skeptical that this will pass in time, but we will give it a shot. I think, yes! All right, and we pass. It is a terrible, terrible algorithm. Look at this. Only beats 8% for runtime. It's great for memory though. It beats 91% for memory, and that's even with making a copy of the grid. Imagine if I mutated the input grid. Whew. All right, so great memory footprint, but terrible runtime. Now, there are some things we can do to improve this, but I don't think they're really gonna hit the 100% mark. I think we need a completely different algorithm. One thing we could do is, we're calculating these lengths over and over again. We could pull some of these out into variables. Same thing up here, we could pull that out. These maximums, we could maybe move this result into our loop here, but it might break because of this double checking right here might cause issues with our result getting set to some high value initially that only gets overwritten later with a lower value. So that's one potential drawback with putting the result inside of this loop. The other thing that we're doing here, we are going through the entire grid every single time. Every pass we go through, we check every square in the grid. This isn't strictly necessary. You could use a very similar algorithm to this, but instead of going through the entire grid every time, you would create a stack, or you create a queue, some data structure that will hold just your land to start with. So you just store all your land grid coordinates in this stack. Then you pop your land off the stack, you check up, down, left, right, same thing like we're doing here, but this time you're only looking for water. If you find some water, then you can essentially keep track. It's very similar. You'll keep track in the grid that you found some water. You will replace that water with value +1. It's exactly what we're doing here, but this time you'll push that newly formed land coordinate onto your stack. So instead of going through the entire grid every single time, you're only going through the land grid and you're only going through the newly formed land every time you create new land. So that will probably reduce the overhead of this runtime significantly because you won't be doing the entire grid every time. You're only doing land cells. Okay, I am out of time. I talk too much. I know this one is, it says it's medium, but I think this one's a little bit harder than just a straight up medium. Okay, this was our submission. This is our terrible algorithm. See if you can do better. I bet you can. I'll leave that as an exercise to the viewer. All right, check this one out. Again, this is LeetCode 1162, as far from land as possible. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can definitely do better than I did.